Welcome to part 2 in our mechanical vibrations lesson. Here's an example. A body with mass m being 1/2 kilogram is attached to the end of a spring that is stretched 2 meters by a force of 100 newtons. It is set in motion with initial position x sub 0 being equal to 1 meter, initial velocity v sub 0 being negative 5 meters per second. And we want to find the position function of this body as well as the amplitude, frequency, period of oscillation, and time lag of the motion. So the spring constant K. And this is going to take that 100 newtons divided by 2 meters. So this is 50 newtons per meter. And this allows us to build our differential equation to be 1/2 times the second derivative of x plus 50x is equal to 0, which we could then multiply by 2 to get rid of that fraction to make x double prime plus 100x is equal to 0. So the circular frequency that we would have, circular frequency, all right, this would be omega sub 0, and that is the square root of 100, aka the initial force. So this is 10 radians per second as that measurement. And the oscillation that we would have, the period for that, would be t is equal to 2 pi over omega sub 0. So 2 pi over 10, aka pi over 5. That is about 0.6283 seconds. And the frequency would be v is equal to 1 over t, that being omega sub 0 divided by 2 pi. So this is 10 over 2 pi, or 5 over pi, and that is about 1.5915 hertz. So based on our initial conditions, x of 0 is 1, and x prime of 0 is negative 5. So we could then produce ourselves our general solution to be x of t is equal to the a times the cosine of 10 times t plus b times the sine of 10t. And the first derivative of this function gives us negative 10a times the sine of 10t plus 10 times b times the cosine of 10t. And if we go through solving that, we get a value of a to be 1 and b to be negative 1/2. So what does that mean for our equation? Let me erase through this, and then we could continue then with the rest of that to give our particular solution and answer the remainder of the question. So with our value of a to be 1 and b being negative 1/2, we could then write that particular solution, once I get rid of all this. Okay. So we could write that particular solution as being, in our case, x of t is equal to the cosine of 10t minus 1/2 times the sine of 10t. And the amplitude that we have would be c is equal to the square root of 1 squared plus negative a half squared. If we toss that expression into a calculator, we should get 1/2 times the square root of 5 meters. And the time lag, for us to find the time lag, let me phrase it that way. Time lag. We need to take x of t to be equal to the square root of 5 over 2 times 2 over the square root of 5 times the cosine of 10t minus 1 over the square root of 5 times the cosine, times the sine in this case. This is the sine. Times the sine of 10t. So that simplifies to be the square root of 5 over 2 times the cosine of 10t minus alpha. So our value of alpha there, this must satisfy. This must satisfy the cosine of alpha being equal to 2 over the square root of 5 which must be greater than 0. And the sine of alpha is equal to negative 1 over the square root of 5, which, well, is negative, so less than 0. So we are in quadrant 4. Is what that tells us. So alpha for this would be equal to 2 pi plus the inverse tangent of negative 1 over the square root of 5 divided by 2 divided by, let me make that more readable. One moment. 2 divided by the square root of 5. And there we go. So this is the same thing as 2 pi minus the inverse tangent of a half. So that makes about 5.8195. And our time lag delta, this is alpha over omega sub 0. So in our case, that would be about 0.5820 seconds. So to give a full equation, this will be x of t is equal to 1/2 times the square root of 5 times the cosine of 10t minus 5.8195 based on this particular example. So now the free damped motion, this is with damping but no external force. Our differential equation becomes m times x double prime plus c times x prime plus kx is equal to 0. Or we can slightly simplify that, divide by m and change variable names. K double prime, x double prime plus 2 times p times x prime plus omega sub 0 squared times x is equal to 0, with omega sub 0 being the square root of k divided by m as the corresponding undamped circular frequency, and p being c divided by 2 times m, and that's greater than 0. So we have a characteristic equation r squared plus 2 times pr plus omega sub 0 squared is equal to 0. We have our roots being repeated, negative p plus or minus p squared minus omega sub 0 squared to the 1/2 power. And depending on that sign, we could have differences. with this particular calculation. The critical damping C sub CR is the square root of K times square root of 4 times K times M. So these particular cases, depending on those values, it's overdamped if C is greater than that critical damping. So C squared is greater than 4 km. If C is relatively large, we have a strong resistance in comparison with a relatively weak spring or small mass. So this produces negative real roots. The position function takes that linear combination C sub 1 times e to the r sub 1t plus C sub 2 times e to the r sub 2t. If we're critically damped, if the value of C is equal to that critical damping number, then C squared is equal to 4 times Km. We have equal roots of negative P. The general solution is e to the negative pt times C sub 1 plus C sub 2 times t. And since that's greater than 0, then our position function has at most one positive 0. So that body passes through the equilibrium position at least once. It's underdamped if C is less than the critical damping number. So C squared is less than 4 times Km. We have two complex conjugate roots of the characteristic equation. Negative P plus or minus I times the square root of omega sub 0 squared minus P squared, with general solution of e to the negative pt times a times the cosine of omega sub 1 times t plus b times the sine of omega sub 1 times t, with omega sub 1 being essentially the square root of 4 times km minus c squared divided by 2m. So using that cosine addition formula, we could slightly simplify this to the position function just being nicely x of t is equal to c times e to the negative pt times the cosine of omega sub 1 times t minus alpha, with c being the square root of a squared plus b squared. Cosine of alpha is a over c, sine of alpha is b over c. So with the underdamped case, we have the solution representing exponentially damped oscillations of the body around its equilibrium position. This graph lies between the amplitude envelope curves. X is equal to positive and negative c times e to the negative pt, and touches when omega sub 1 times t minus alpha is an integral multiple of pi. So despite not being periodic, it is useful to call omega sub 1 the circular frequency or pseudo frequency. T sub 1 is 2 pi over omega sub 1 is the pseudo period of oscillation, and c times e to the negative pt is the time varying amplitude. And the action of this dash pi has at least two effects. It exponentially damps the oscillations based on the time varying amplitude, and it slows the motion. So the dash pi decreases the frequency of the motion. So that's part 2 of this mechanical vibrations lesson. Be on the lookout for part 3. Thank you.